So good morning, everybody. So you might be wondering if you have the management consultants up, we're probably already at the peak of the hype curve. And I apologize, but we might not be as clueless as you think, but I mean, in general, we're really up here because as a reflection of the enormous amount of interest there is in all the business community on quantum computing. Both in the kind of application community to say, okay, what is the potential? I think it has earned its bullet point in the innovation roadmap of every single company in the world, as well as obviously on the technology side, what is really the market potential. We do actually, I mean, we are lucky to have a very talented workforce that comes from everywhere. So, you know, when I started to work on quantum computer BCG, I found that we have PhD in every single technology, right? I mean, we have people who did, you know, superconducting, who did ion traps, but even, you know, people in photonics and silicon-based technologies. So I think we try to, you know, really work with the community and say, okay, what is really to give a review of the field. In one of our reports, we really went, you know, through everything aspect of the field, but then obviously focus on the market potential. And I think contrary to Bob, we want to focus more on the market potential today when we go forward. Now, I think I will skip the introduction. I mean, you all know the basics. So for me, I mean, I'm actually a quantum physicist by background. I got my PhD at MIT in Eddie Forest Group, so but not working on quantum computing at the time. But clearly, you know, the fact that you have, you know, the superposition, so you can point in every direction, not just up and down in a simplified version, and that states act as a group, give you a potential exponential information density. Everyone can follow that part and say, okay, it's really interesting, so how do I work with that? And most people understand it's really hard to feed it in and to read it out. But that's about the level of understanding of most people in the industry, and they say, okay, so what's up now from them? And then you get these wonderful promises. I put two up, pharmacy. We indeed put out today a hopefully well-founded report on what's the potential in pharma. But you get the case, so if you can model all kinds of atoms and even nicer in all kinds of chemistry, you save, you know, the world in very easy ways, which is obviously true with a fully quantum corrected quantum computer, which we think is too far out for us to focus on at this point in time. So we say, okay, what is really the near-term potential is our core interest. Now, I would say though, we looked at it a month ago before the Madrid COP26 conference and found it quite interesting that if you look, one of the earliest applications is in chemistry, because I think for lots of reasons, chemists are well prepared. They know quantum, there's no computing, which is nice. Secondly, there are lots of active centers of catalysts that have an interesting size, let's say 100 molecules or so, where you think you could, you know, potentially approach them. And if you look at a lot of them are actually incredibly important for climate change. I mean, you have, you know, catalysts in H2 production, in photovoltaics, in electrodes, obviously Femico in kind of alternatives to the Haber-Bosch process of fertilizers, which would also save, you know, 3 to 5% of CO2. We can't wait for them, but it does obviously increase the interest in saying, okay, you know, this would really be a technology that could help in very fundamental problems going into the future. Now, it's very confusing when you think about, so to say, the short term and the applications. And perhaps let's give you one structural chart, and then I will hand over to my colleague who will lead you, you know, how do we actually approach market sizing? Because you can put wonderful hockey stick numbers everywhere, and I think the numbers are frankly meaningless. So we'll lead you know, what do we see as trigger points and milestones that are important in order to reach those? And you know, depending on those trigger stones, what applications become available. I mean, let me perhaps point out that, I mean, as Bob just said, I'm totally convinced we're not at the Moore's Law stage. We cannot yet, you know, the current technologies will probably not scale. Or let's say the current technologies, I mean, neither superconducting nor ion traps. I mean, they know what they would need to do, how to scale, but not how they would actually do that, what they would need to do, how to scale. I think, you know, both photonics and spin-based are very interesting. We will have scaling technologies, but we're not yet at the transistor stage. So you cannot, you know, any paper that starts, I assume that it doubles every 2 years or double exponential or whatever. I think you can safely put away. I mean, because it's not worth yet, your time for the conclusions. Perhaps just one chart where I think we actually are, and why the next years are so uncertain, but also so interesting at the same time. And strangely, that has to do with algorithms. We're consultants, so we simplify terribly. So I apologize for all these Adam and all the other speakers that are going to talk about a profound way about algorithms. We put it in a 2x2, obviously. As BCG, we put everything in the 2x2 matrix. So we said, okay, we have two kind of criteria. A, the speed up potential. What can you actually prove in terms of speed up in particular? And B, how robust are algorithms against noise? And the nice thing, if you put them at 2x2, they kind of get it. So all the famous algorithms, the Shor, the Trotters, the HHLs, and so, are wonderful. You can prove fantastic speed up. Sadly, they are very noise perceptive, so they can't take any noise. You need essentially a noiseless environment or quantum error correction. So we call them purebreds, right? You take the horses. So they can run very fast, but you can't disturb them. And there's a whole type of other algorithms, and they are very different in their specific parts that are reasonably noise resistant. We know how to deal with them. All the variational algorithms, all this, QAOA and so on. I mean, we know how to deal with noisy environments. You can keep them short. You can mix them with other stuff. Even, adiabatic quantum computing I would put in that category. However, it's very hard to prove any speed up. So you just don't know. Now people say, well, that's horrible for if you are a scientist, but frankly, if you are a practitioner, you don't particularly care. I mean, I actually worked a lot on artificial intelligence, and I remember, Minsky's devastating paper, on that stopped neural networks for a long time, essentially because he said you can't prove anything about them. And he was right. It's very, very hard to prove anything about it. It didn't stop them from, breaking through in 2012 and solving essentially vision and speech. And now you're starting to try to understand why they actually work so well, and it's still extremely hard to prove anything about it. So not being able to prove anything, I don't particularly care. I mean, I think it's wonderful because it actually poses interesting problems. But it's clear that, these algorithms, it will be an experimental problem, how well they work over the next few years. And it's clear enough ever since, say, the quantum supremacy, I think, was a great breakthrough because it's seen that in some problems you're starting to get at a realm where you can do something. Lots of people get very interested and say, okay, so where would that be and where should I watch out for and what kind of structures we have? And I think we can address that to some extent. I think there's still an enormous possibility for opportunity space for algorithmic innovation. So I think this is very incomplete. But that's why companies are really interested in to say, what could happen during the next years and why, we want to get into the game. Now with that, I hand over to Matt, who will lead us a little bit through how do you actually try to size markets given this uncertainty and properly reflect both the short-term and the long-term potential of the markets. Matt.
Thanks, Philip. Yeah, so we did kind of relax some of Bob's reservations and did attempt to size the market and understand, in the spirit of practical quantum computing, what kind of value would accrue both to end users and to tech providers, and when. And I think, look, in an endeavor of this kind, the only thing we can be absolutely certain about is that we got it wrong. And the question is sort of how and where. But I think that the goal is less to look at a point in time and understand if we got it right or wrong, and place a bet on the technology in a given use case, so much as to dimensionalize the pools of value that exist in various industries and use cases right now based on computational bottlenecks, and to try to understand and to triangulate expert opinions as to where quantum computing can relieve some of those bottlenecks. Speaking of which, in order to build out our opinion, we talked to about 100 folks, 60 interviews or so from external experts within business and academia. We had internal experts, again, some technologists, but many who operate, in different industry verticals. Of course, we read all the research. And I think what we were trying to do is triangulate two kinds of expertise. There's one in terms of quantum hardware and algorithms, right? So technologists, and that's a certain type of expertise that we're trying to bring to bear. But then there's also just industry expertise as well. Folks that understand where the real pain points are in industry and where, what kind of value and opportunity costs, et cetera, are associated with those, right? So, like, how long does the assay process take in drug discovery? What kind of performance testing? What does performance testing cost in materials design? How much capital reserves are held by banks because they can't do tail event risk simulations? It's all these sort of things. And so what we ultimately did is we talked to all these folks and really prioritized 4 industries: materials, biopharma, financial services, and then computational fluid dynamics, largely in aerospace and automotive design. We did so in large part because, of course, we thought that there was a lot of value in these industries, and these are the ones that you see come up quite often. But also we thought that some of the value in these industries was kind of nearest to hand, in large part because of, for example, in materials, there's a lot of folks in the industry with pre-existing expertise. Sometimes there's a good deal of fit, right, with existing algorithms and computational bottlenecks. And so we prioritized these use cases, and then we ultimately scaled it up to get a view of the full market. Before hopping into the numbers, I did want to just deliberate for a moment on some of the problem archetypes that quantum computing is capable of solving. And like at a glance, it looks like just sort of 4. It looks sort of narrowly defined: combinatorial optimization, differential equations, linear algebra, and of course factorization, which you hear about most in the press. And I think the thing I'd like to emphasize is that from this sort of narrow space of problem archetypes, there actually opens up an enormous set of industrially relevant use cases. So while it seems like, okay, just these 4 problems, there really are an enormous number of applications and a tremendous amount of value, as we'll show soon. And these are, when we think about these archetypes, if you think of combinatorial optimization, just to take an example, this is like the traveling salesman problem, right? Where you look for the most efficient route through a given number of cities, returning back to the original point. And I think the thing I would like to just mention is that this is actually extremely easy to do. You could almost do it by hand with a small number of cities, right? But with each additional city, each additional dimension, it actually increases in complexity exponentially, right? And that's what's called an exploding state space. So a lot of the problems that you see here are defined by this characteristic, that they have an exploding state space. Quantum computers are able to scale exponentially, as Phillip and others have noted. And so when you look around these problems, right, so for combinatorial optimization, you could imagine like whole businesses are effectively built on this, right, with network optimization, FedEx, Uber, et cetera. Differential equations, we talked to folks in that do wind tunnel testing, right, for airlines that spend $40 billion a year on wind tunnel tests across all industries, right? Linear algebra, of course, again, we talked a little bit about risk management in finance, and then of course factorization, where you have Shor's algorithm that obviously gets a lot of the mass media frenzy. Great. And let me just take an example of how we built it. I had mentioned that we took 4 prioritized use cases to give a little bit of depth, and then I'll show you a little bit how we kind of built it. It starts with a static picture of the existing workflow. So you take a look. What you have here is materials design, and on the left you have these basic research, all the way to synthesis to testing, and on the right you have manufacturing, commercialization, et cetera. What we did is we looked at the workflow. We broke it down into its various modules and stages. We then talked to experts who gave us the kind of pain points at each stage. we understood the spend, so there's $40 billion in spend annually, globally, across just these three, candidate material selection, material synthesis, performance testing. And then we talked to experts who could help us understand where quantum computing could intervene in a value unlocking way across this workflow. That's sort of this static view, right? And what we understood were 5 core sources of value. So there's efficiency in design. You can just reduce this $40 billion in spend, right, with more efficient, computer simulations. Then, once you have a more efficient process, there's follow-on value because you have accelerated time to market. So there's faster revenue realization. Of course, there's the promise of potentially net new materials, one of which, sort of ironically, is room temperature superconducting, right? So strongly correlated systems like that. There's also potentially better materials, so improvements on existing materials. And then there are materials that just synthesize a little bit easier. So while most of the value we think will be in this R&D phase, if you do actually come up with, say, a material that has kind of a more flexible or broader tree of potential synthetic routes, that will obviously have value downstream as well. And I think one of the things that in doing this exercise, and we've of course worked with companies to look at their workflows, one of the things that we always want to make sure that we're emphasizing is just the degree to which you have to be comprehensive about this, because certain improvements in any point in the chain can have a lot of flow-down effects, and a lot of the value actually comes from that. Great. And what we've done here is layered in the time dimension. So a lot of this is, okay, so but when? And you'll see that we have kind of 4 periods here. We have the near term, from now to the next 5 years. We have the late NISQ era. We have broad quantum advantage, which is defined really by principally error correction. And then full-scale fault tolerance, which is error-corrected architectures at scale. And what we did is, if you look at the y-axis, you have the value created. And by the way, when I say value created, this is the value that will accrue to end users of the technology. So the BASFs of the world, not the tech providers necessarily, which is IBMs and Googles, et cetera, but to the end users, so value created. When you think about translating that to value capture, it's typically something like a tenth, right? So it actually is quite a difference. But you have value created on the y-axis, and on the x-axis, you have quantum solution maturity. We don't articulate it exactly in terms of time. We give kind of rough time estimates. And that's broken out in 2 ways. One, there's sort of quantum technologies like error correction, error mitigation, some data compression type techniques. And then there's solution-specific algorithms. And those will actually change by use case. Anyway, this is sort of how we did the sizing, and I think one of the things that it gives you a little bit of a sense of is that, while it starts with things like, local multi-body interactions, so that you might have a kind of CAD sort of assistance in designing a unit cell of a battery, what you have on the other end of the spectrum is like the kind of full promise of quantum computing with, strongly correlated systems, and room temperature superconductors, et cetera. Okay, and I think just the one thing I'd like to just point out on this one, kind of to Philip's point, it's that the path to value is sort of dotted with these potential step changes. It's not a linear curve, or it's not a simple linear curve, right? There are these step changes, I think, that will unlock pockets of value. And what we did here is we looked at specific materials that we think would require certain amounts of, like sort of qubit strength, et cetera, and largely used quantum volume as an underlying metric. But that's how we actually built the curve. Right, and when you take it, like when you broaden it to the whole, across industries, you get a similar shaped curve, of course. I think the thing I'd want to just emphasize here is that while we think, like the massive value, the 450 to 850 billion for end users, will take time, right? Will be the promise of full-scale fault tolerance. There is a lot of value in the near term itself. And as I mentioned, we picked some of these industries here because they actually, while they kind of blossom late, they do mature a little bit earlier for a number of reasons. And just from near term to full scale fault tolerance, if you take, for example, finance, right? If you do, obviously you have kind of high frequency trading strategies that can be enacted once you have kind of linear algebra simulation types. But even in the near term, if you think about portfolio optimization, a lot of the algorithms now that perform portfolio optimization actually ignore things like non-convex, non-concave surfaces for the optimization. So things like interest rates, lots, trading, transaction costs, things like that. Transaction costs can be 2 to 3% of all assets under management. So these are really, really significant pockets of value that are there for the taking in the next 3 to 5 years. The one I would want to mention before handing back to Philip is just that it may be the case that the first place that quantum computing creates value in an industry might actually not be on a quantum computer at all. There are quantum-inspired algorithms, for example. There are computer-aided drug design approaches. There's a lot of activity in the startup space related to these as well. And so I think obviously we have the normal path to value that's defined on top of quantum technologies, and that's what we focused on in our last value creation report. The one that's coming out today will actually have a little bit on some of these quantum-inspired techniques as well.
Thank you very much. So let's perhaps very briefly to see how do you actually play in this market, give you a few ideas, and then I hope to open it up to questions which might be more interesting. So very simply, for kind of the user community, we say it's very simple. You want to do two things. To really conduct what we call impact on quantum, in terms of really a diagnostic around what you did, a little bit similar to what Matt just demonstrated. Where could it actually be? And I'll give you a few ideas, what to look out for. And then to say, how do you actually co-innovate? And clearly you want to have one of the tech players. There's a huge ecosystem out there, so it shouldn't be very hard to find someone who would be eager to work with you. On the self-assessment, right? I mean, we always say, well, obviously, if you are in high-performance computing, that's wonderful because you can look at where do you spend your resources and where do you think these efforts yield low impact, delayed, piecemeal results. Financial community is very frustrated in some of the parts, and so are other parts of this world. The other thing is obviously where you think it's too complicated to simulate, and I think the third, where this is particularly important, if you spend lots of times in either wet labs or physical prototyping, right? Lots of things, and I work also a lot in AI. I think if you take everything, lots of real-world processes become accessible to simulation, and quantum computing is obviously a very effective part, in particular if it is a very strong computational aspect to it. And then, there are just the archetypes that Matt just mentioned: simulation, optimization, partial differential equations, whatever you have, that are typically, easy to solve or easy to. We have classical ways of attacking them with a quantum computer, and you have to see, how ripe is it. It's hard to get used to that. I mean, a company I like very much is OTI Lumonics, and they do quantum computing, they do OLEDs, small company. But they really make a lot of effort. They are in computational thing, in classical computational chemistry, and they don't want to be surpassed. They make lots of efforts to say, how would we approach them with an ANILA? How do you approach them with quantum-inspired solutions? How would you approach them with gate-based solutions? And have very interesting results, where they made most progress. And they say in the end, it doesn't have to be better in a way. It has to be better, but it can be better in many dimensions. It can just be cheaper. It's actually rather easy to access these things over the cloud today compared to HPCs. It can be faster, or it can just provide you a new way of looking at a problem that is just a different angle. And then someone else can prove you could have done it, with your traditional methodologies, but you don't particularly care. Clearly, you want to work with hardware, with some kind, not a hardware, but with some kind of technology provider if you're a user. To really build something that's credible and that's as a proof point. cross-skilling, to make your people understand how to approach things. I mean, if you ever looked at how Shor solved cryptography, I mean, it's rather trivial, if you know a few things about the mathematics, but it has nothing to do with calculating faster, just nothing. It just, essentially he solves it by interference, right? I mean, it's a totally different way to find, hidden symmetries in problems and then to solve it in a different way. And that's really things that lots of computational groups are not used to. We have a huge AI analytics group, and we're just starting the quantum computing part, because in some of the optimization problems, clients want to learn about it because we also train clients, but we also say, okay, there are actually interesting angles to it. Then obviously lots of companies are interested in, can we secure any IP? It's not very easy on the application algorithmic side, but clearly. And then obviously, to access the entire market and networks, particularly if you're more on the technology side, there are huge networks out there. On the right-hand side, I give you, this is a very, very simplified view of our ecosystem chart, where we say you end-to-end providers, hardware, software, and specialists. We put out as a service to community, huge maps of these things, so you can actually orient yourself, who is doing what in this ecosystem and who might be a great partner for you in moving forward. Let me perhaps mention just, three things that we put out there that are by far our most popular reports. So, and I always say it depends on what kind of problem we have. One problem I have, and some of you might have, people constantly ask me, what is quantum computing? And I'm really, really sick and tired of explaining it. So we put out this quantum computing test. We put essentially an educational introduction as a quiz, and it's very popular. I constantly get messages on LinkedIn. I have 12 points on the quiz. I have 11 points on your quiz. I don't know what. You actually can cheat. You change the answer afterwards if you really want to have full points. But I think it's a nice way to, if you ever have friends and family, lead them to the quiz. They will have fun and go through it. The second is really, the first time we did a big review of the field, the next decade of quantum computing, how to play it. And I have to say, I'm incredibly grateful to the community. I think about half the speakers of this conference contributed, the entire West Coast, but all over the world. I think the community is still incredibly open to share and to extend it. And we really looked at, everything from ecosystem, obviously, who are the players, how do you structure them? Then, regional differences in publications, IP, and companies, and there are always some surprises. The biggest surprise, I think, if you compare with other technology landscapes, I mean, China, US, Europe, Canada is always there. But for example, Australia is huge in quantum computing, right? I mean, they make this effort. They have a national program. We want to lead quantum computing. We miss semiconductors. We want to lead quantum computing, and Michelle Simmons, one of the leading quantum physicists, became Australian of the Year last year, right? I mean, that is unmatched in any other geography. On the other side, you have a surprise. Israel was essentially absent. It was really amazing. And Israel actually had the biggest skeptic, Jill Kalai, who I think is starting to give up after the Google experiment, but I'm not sure. He had a serious criticism about, could there be a surprise with, strong correlations so our estimates don't work? But I think they were convinced by Google because they just announced a huge quantum computing program, I think 2 weeks ago. So a huge national program now to catch up. But a nation that typically leads in this. And then we looked really at all the hardware technologies, from annealing to all the standard technology, and compared them along the dimensions you would have, the qubits, gate fidelity, scalability, et cetera, et cetera. So you get a little bit of sense, what is interesting and what not, and then at the whole algorithmic zoo that you will hear a lot about this, and then really how to play it, to say what are the applications and what to do it. So I'm really incredibly grateful. And the other report was what Matt drew a lot, where will quantum computing create value? We did lots of go-to-markets for the large tech players, and we have our own research, but some of them were actually also kind enough to allow us to publish, because they want the community to move forward. So they say you can publish part of the results. And that's why you see these very detailed roadmaps depending on you know, what happens and what doesn't happen. And we have it for every single industry. We put it out in the public for the most relevant, and I hope to do a favor to the community. I think overall, I mean, this morning actually we published Biopharma. It's just a small report, but we thought, you know, we had so much questions from pharma, you know, we said if chemistry is there, why is pharma not there? I say, okay, we'll tell you a little bit about pharma. It's a little bit further out, but I think it's also very interesting. So you know, any interest and so on, you know, come up to us anytime. We're very committed to this BCG, but perhaps there's time for one or two questions. Thank you.
Hi, thanks for the talk. I was wondering if you could say a little bit more about the technical basis of the idea that computational fluid dynamics would be a viable application in the next 20 years. That one strikes me as a little unusual. As a scientist in the field, I don't see people talking about that application very much. Somewhat naively, it seems like the number of degrees of freedom you'd have to represent to solve, you know, an aerodynamics problem to sensible accuracy would just be so huge that it couldn't even fit on a first generation of fault-tolerant quantum computers.
Mm-hmm.
I think that seems like a good question, and I think I'd love to discuss it. It might be a little bit long for, I think we're kind of timing out here, but if you can catch me afterwards.
But I can tell you one company that is very interested in that and is doing it is Airbus, right? Mm-hmm. So I mean, clearly, because for them it's obviously very important, and the time frames for them are so long that they actually say, well, if it's relevant for, you know, in 10 years, we actually, you know, I mean, as you might know, aeroplanes have horribly long time frames. So that's why, you know, look, the companies that have these long time frames are the ones that are most active right now. That's why also, for example, the financial institutions right now worry about cryptography. Not because they think it will be broken in the next 10 years, but they said, but we will need 15 years to adapt. We need typically, you know, 8 years to take a decision and 8 years to actually adapt. They think of the year 2000, right? So they're actually starting to prepare. They don't know what the solution will be, you know, what algorithm they might accept, but they're starting to prepare to be able to switch in case they want to switch. So these kinds of preparatory parts, companies have very long time frames that look at that very intensely right now.
And I guess the thing I would say there is that, like, what we've seen so far is that companies are starting with mesh optimizations that could fit in kind of an ANSYS flow, but it's mostly that first stage right now.